Densities. From black holes to blivits. Hydrogen, helium, and oxygen are so light that gravity can't hold it all, and some of their airborne molecules float into space. They leave Earth's atmosphere. Tons of these gases escape each day, but don't worry, we'll never run short. Water is one of our universal measuring standards, and so 1 liter of water has been designated to have a mass of 1 kilogram, or about 2.2 pounds. Heavy water is another term for deuterium, which is so named when 2 hydrogen atoms of a water molecule are each fused with 1 neutron, as opposed to no hydrogen neutrons for regular drinking water. It is not radioactive, and it is safe to drink occasionally, but long-term ingestion of deuterium may inhibit the cell's abilities to repair and replicate DNA. Tritium, a hydrogen atom with 2 neutrons, is radioactive. The extra neutrons make the molecules denser. Limestone is composed of vast accumulations of seashells. To be specific, the calcium carbonate exoskeletons of marine animals are transformed into sedimentary rock through compression and time. Over the past eon of relentless mollusk and crustacean deaths, these mounds of shells have piled up to become rolling hills and even mountains. Basalt, a volcanic rock, is denser than limestone and flows from the Earth's mantle and hardens to become the tectonic plates. Granite is its lighter cousin and floats atop the basalt to form our continents. Both types of rock are incredibly strong for their densities. Balsa is the least dense wood at 0.11 grams per cubic centimeter. The Janka wood hardness test determines hardness by measuring the force in pounds to embed a steel ball halfway into a wood sample. The ball is 0.444 inches in diameter. Balsa is also the softest wood, needing only 70 pounds of force to embed the steel ball. The densest wood is lignum vitae at an average density of 1.3 grams per cc. It's heavier than water. The hardest wood, according to the Janka test, is Australian bull oak with a resistance of 5,060 pounds. Wood is not very dense when compared to the average animal density of about 1 gram per cubic centimeter. Trees are porous, but they have cellulose cells, which make them much harder than animals. When subjected to Brinell indent testing, which is the metal version of the Janka test, rock-hard maple was found to have the resistance of lead. Hickory is hard as tin, and lignum vitae is even stronger. However, even the hardest wood, Australian bull oak, is softer than aluminum. Still, to put those wood hardnesses into perspective, it's impossible to drive a nail through rock maple with a handheld hammer. Either a powerful nail gun would have to be used, or the nail holes would have to be pre-drilled. Metals are the densest elements found on Earth. On average, they don't have the uncanny hardness of the minerals in rocks, but they are much more versatile in building and manufacturing. Metals have high tensile strength, which is resistance to breaking under tension. Rocky materials are usually brittle. Remarkably, A36 structural steel has about 200 times the resistance to breaking than unreinforced concrete. Osmium is the densest of all elements on a periodic chart. This element has 255,000 times the density of hydrogen. It's amazing that we humans can overcome the difficulties of working with both elements and those in between to our benefit. We still have a long way to go in the understanding of electrons and atomic nuclei, but we're getting there. Now we come to densities that challenge our comprehension. We often read articles in science books that claim mind-boggling numbers, but until we feel it or see it, most times these amounts are meaningless. Nevertheless, when it comes to the unbelievable, we'll all agree that nuclear densities top the list. Stars are the place to start. When these gaseous spheres come to the end of their lives, The outward push of their nuclear reactions can no longer stay in equilibrium with the inward pull of the gravitational force. This results in an implosion. These gravity-induced contractions force the star's atoms to compress until gravity and the nuclear forces repelling the gravity are once more in equilibrium. The results vary, but in all cases, an atom that occupied a defined space now occupies a smaller space. The same atomic mass now occupies a smaller volume. Thus, the atom has a greater density. Atoms are almost entirely empty space, so quite a bit of compression is possible if there's anything strong enough to compress them, like gravity. There are balls of hydrogen out in space that are too small to become stars. Anything less than 1/2 the mass of our Sun usually can't attain the internal temperature to sustain large-scale fusion. These low-mass red malcontents simmer at low temperatures for the entire lifespan of the universe. It's theorized that stars between 0.80 and 8.0 solar masses, and our Sun is 1.0 solar masses, will eventually collapse to form dwarf stars that are white hot, hence the name white dwarf star. When one of these stars is in its death throes, a considerable amount of solar mass is shed to form a gas cloud called a planetary nebula. The remaining mass is squeezed down to create the white dwarf. Gravity will force the electrons of the individual atoms to orbit closer to their nucleus. If the remaining mass of the star is less than 1.4 solar masses, then the electrons will not get close enough to touch the protons or neutrons. The masses of the atoms will remain the same, yet function at a smaller volume. The atoms will be denser. It's calculated that a star of 1 solar mass will lose about 1/2 of its mass, and the other 1/2 will be compressed to the size of the Earth. That's 65 million pounds per ounce, or 1 billion kilograms per liter. Water weighs 0.0625 pounds per ounce, or 16 ounces to a pound. Stars that are larger than 8.0 solar masses, but less than 30, will end their lives in supernova explosions. Most of the star's matter is blown into space, with between 1.4 and 3.0 solar masses remaining. The gravity produced by this much mass will force the electrons of the atoms to fuse to the protons in their nucleus, thus forming neutrons. Instead of atoms containing protons, neutrons, and electrons, there are only neutrons. These neutron stars have the same density as a neutron. And that begs the question, what in the world are protons, neutrons, and electrons made of to be so dense? If the entire Sun were transformed into a neutron star, it would be a ball about 8 miles in diameter. Anyway, there are big stars out in space. There's lots of room to grow. Some astronomers have suggested that the Milky Way galaxy might be even more expansive than the great state of Texas. When something, about 30 solar masses or more, collapses, gravitational forces will squeeze atomic nuclei even further. Neutrons are made of 3 quarks, and the spaces between the quarks are either partially eliminated or completely. This density forms a black hole, at least in theory. It's black because escape velocity exceeds light speed, so light is bent back toward its center. The density depends upon the physical size of the black hole, and contrary to what most people think, the smaller the denser. If the Sun became a black hole, it would only be 3.67 miles in diameter. It's theorized by some that black holes are denser than quarks. The implication is that quarks are not fundamental particles. I wonder if interest in black holes has transcended mere science and turned thoughts toward mysticism. For example, no object should be able to enter a black hole until infinity is reached. Until the 12th of never, and that's a long, long time. Nothing with mass can penetrate the event horizon in a finite time span. Yet scientists who are interviewed on television programs are forever talking about matter entering black holes and traveling through wormholes. And let's not forget spaghettification. Shut up. If scientists can't even agree with each other, then the public doesn't stand a chance of understanding these crazy things. Too much weak thinking by the professionals. Planck density is the end of the line. The German physicist Max Planck calculated many physical limits, such as the smallest units of length, time, mass, and the list goes on. Because of Planck's tireless research on mass and density, his breakthrough discoveries have led to the development of the blivit. Dr. Planck once placed a flaming blivit on Einstein's doorstep upon learning that Albert had won the 1921 Nobel Prize in Physics. Aside from this, Planck density is the ultimate mass-to-volume ratio. Nothing can get denser. It is when an atom is at maximum density and has no space between its particles. It is possible that the centers of the smallest black holes are at Planck density, but that's only conjecture. If the universe truly were the result of the Big Bang, then all the matter and energy was not compressed into a point of infinite mass. The television theoretical physicists are wrong. The size, mass, and density of that pre-expansion universe can be determined without the semantics. Everything that makes up our universe could be fit into a container smaller than a milk carton. Max Planck would have preferred a paper bag, and of course the load inside would have to be at Planck density. Thanks for watching. Talk to you soon.